quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Good evening, everyone. It's great to see a full house here. My name is Ed Hines. I'm a physicist from Imperial College, and I'm here to introduce the prize winner this evening, Debbie Jin, whose work I've followed from, well, I'm old enough to say I followed it more or less from the beginning. And so, by way of introduction, let me just tell you a few things about Debbie that she would be too modest to tell you herself. She graduated from Princeton University and got her PhD from the University of Chicago. She is now a fellow at the National Institute of Standards and Technology, which everybody calls NIST in America. That's the American equivalent of the National Physical Laboratory. And she's a professor at the University of Colorado. She leads a group in JILA, which stands for the Joint Institute for Laboratory Astrophysics. JILA, I would say, is a leading institute, possibly the leading institute, for atomic physics. In 2003, her team made the first Bose-Einstein condensate of fermionic atoms, that is to say, atoms whose spin is a half integer. Probably most of you know that particles with integer spin are called bosons, and they have the property that they like to all do the same thing, and when you put them in that state where they are doing exactly the same, that's called a Bose-Einstein condensate. So what she did was make a Bose-Einstein condensate without using bosons. So this is an interesting and important achievement. And the trick is to make these fermions, which have half integer spin, pair up. Once they make a pair, then the pair has an integer spin, and then after that they're able to Bose condense. So she made the first exploration of what happens as the atoms cross over from being separate fermions to paired up bosons. And in the course of that, she developed and perfected the use of something called Feshbach resonances, which allows one to control the interactions between the atoms and how strongly they interact with each other. Some people have noticed that this pairing behavior is an important thing to study because it's exactly what electrons do in superconducting materials and what helium-3 does in superfluid helium. But the difference with the atomic gases that Debbie has developed is that you have tremendous control over all of the parameters of the system, including, as I told you, the strength of the interaction between the particles. So this makes her lab has become a kind of test bed for understanding and studying how particles interact in this kind of quantum many-body system, and do the fermions pair up and form a Bose condensate. In a separate experiment, she's looked at how bosons interact, how a Bose condensate made of bosons works when you control the interaction between the particles. And she was the first to demonstrate and measure a thermodynamic property called contact, which was theoretically predicted to be something that you could say general about complex systems with strong interactions. But finally, I want to mention one other of her experiments, which grew out of the study of how bosons interact with fermions. So spin integer and spin half integer interact with each other. And so that's developed in collaboration with Jun Yi, who is also at JILA, into an experiment that has allowed her to make ultra-cold polar molecules with a density and a temperature way beyond what was previously possible. And this has made the quantum gas of polar molecules a really important new research tool. I think she'll probably talk a little bit about these potassium rubidium molecules. With these, she's able to control the chemistry. So if one of these molecules approaches another one, she can put them in a totally defined quantum state and control whether these molecules interact or not. So this is fundamental control of chemistry, which I think is very interesting for a physicist at least, though we were just discussing you're not going to make kilograms of stuff this way. But nevertheless, it's important, I think, for understanding basic things about chemistry. The significance of all this has been recognized by a lot of awards. I'll list you just some of them. In 2003, she won the Physics MacArthur Fellowship, which some people call the Genius Grant in physics. She won the Rabi Prize of the American Physical Society in 2005, Benjamin Franklin Medal in 2008, Gold Medal of the US Department of Commerce in 2011, the L'Oreal UNESCO Award for Women in Science in North America in 2013, and the Comstock Prize of the US National Academy of Sciences in 2014, this year. She has been elected to the US National Academy of Sciences and to the American Academy of Arts and Sciences. Okay, that's a long list of awards, and then there's one more, which is what brings us here today, the Institute of Physics Isaac Newton Medal, which is awarded to a person of any nationality for outstanding contributions in any area of physics. This is the Institute's most prestigious award. Previous winners are John Pendry. I list the names because I think you will know them all. John Pendry, Martin Rees, Leo Kadanoff, Ed Witten, Alan Guth, and Anton Zeilinger. So this is a list where Debbie certainly belongs, and I'm delighted that she's joined the list, and it's my great pleasure now to introduce her to talk about ultra-cold gases.
Okay. Thank you very much for the very kind introduction, and it's certainly my pleasure and honor to be here today and to have a chance to tell you a little bit about some of my research. So I'm going to talk today about ultra-cold gases. It's not going to be a comprehensive talk. I'm not going to talk about everything about ultra-cold gases, but just some of the things that I've worked on. This is a picture of JILA, this Joint Institute of Laboratory Astrophysics. It's a joint institute between NIST, the National Institute of Standards and Technology in the US, and the University of Colorado. All right, so what I'm going to tell you about today is just a gentle introduction to ultra-cold gases, what they are, why they're interesting, extremely little on how we actually make them and manipulate them. Then I'll talk about some of the quantum behaviors that we see, the quantum behavior of bosons and fermions, and I've highlighted the one I prefer. All of this is to get to the point to tell you about the Fermi condensate, which is something that we are continuing to study in the lab today. Okay, so ultra-cold gases. So I'll start with just a little bit of motivation, why you might be interested in what happens at very low temperatures. That's what I mean by ultra-cold, extremely low temperatures. And basic motivation is just that you can see new phenomena if you go to some extreme regime. And temperature is one regime you could look at. You could go to very high energies, like a particle accelerator, or you could go to very low energies or very low temperatures and ask what happens. So just to motivate this a little more, let's look at, say, a temperature at the surface of the sun. That's about 6,000 degrees Celsius. And I want you to imagine that you're a scientist that lives on the surface of the sun. Okay? So this is your ambient temperature. This is what you see every day. You look outside. What do you see? You see everything is a gas or a plasma. But since you're a scientist, you have a laboratory there on the surface of the sun, and you're able to reach much lower temperatures. So now what can you see? All of a sudden you see things that you've never encountered, things like solids and liquids, the things that we're used to here on the surface of the Earth. Okay, so this just gives you an example of if you go to some extreme temperature that doesn't exist in your ambient environment, you might find some new behaviors, particularly of matter. So we're going to start here as this is sort of our room temperature, certainly if you live in Colorado, and ask in a laboratory, can we get to lower temperatures and see what how matter behaves. Okay, so in talking about temperature, it's useful to use a Kelvin scale, so just the Celsius scale shifted so that 0 is absolute 0. And I have a thermometer here marked in Kelvin, but it's marked in powers of 10 or logarithmic scale, so every number is a factor of 10. So if we just put on here the two temperatures we just talked about, we've got our room temperature at about 300 Kelvin, and going up on the scale that far, you get up to the temperature of the surface of the sun. So very different behaviors, changing by that much on this scale. Let's put some colder temperatures on there. The first one I'm going to put on there is the lowest temperature you find in nature. Okay, so that, of course, is in outer space. It's the cosmic microwave background. Not accurately depicted in this cartoon. I actually mean the temperature far away from any astrophysical or human body. But that temperature would be about 3 Kelvin. Okay, so that's about as far down toward absolute 0 as this was going up to the surface of the sun. But in a laboratory, we can reach much lower temperatures, okay, than you can find in nature. And so I've got a mark here at a millikelvin. So several orders of magnitude down. A millikelvin is a very common temperature that you can achieve in the lab. You can do this just by building a fancy refrigerator. So you can see a big steel can there, obviously a refrigerator. This is actually a photo of a group down the hall from my lab in Gila, where they have a refrigerator that they put in liquid helium, liquid nitrogen, cryogenic fluids, and reach temperatures of a millikelvin. And these, of course, are temperatures where you see lots of interesting behavior, things like superconductivity and superfluidity of helium. But today, when I talk about ultra-cold, I want to go down another 4 orders of magnitude down here. So I'm going to talk about a gas of atoms cooled down to about 100 nanokelvin temperatures. Okay, so that's what I mean by ultra cold. This is my cartoon picture of a gas. Obviously, gases are invisible, but we pretend they're made up of little balls, namely atoms, that are flying around in that flask there. Okay, so what new things happen when you reach these very low temperatures with a gas is all of a sudden you encounter that the gas is not classical. So actually, my cartoon here this is a very classical picture, right? We imagine a gas is made up of little balls whizzing around just like billiard balls. That's actually a very accurate picture for almost any gas that you would encounter, but not for an ultra-cold gas. So the ultra-cold gas behaves quantum mechanically. So it is a quantum system. So quantum mechanics and quantum behavior is something that we're familiar with, but usually we associate it with lighter particles. For example, an electron. Okay, so an electron, either in an atom or maybe in a metal, behaves quantum mechanically even at room temperature. And this is because the electron has a very small mass. An atom, on the other hand, is very heavy. So why do we have to go to such low temperatures to make a quantum gas? It's because we want the atom itself to behave quantum mechanically, not the electrons inside the atom. Okay, so the whole atom. That atom might be 4 or 5 orders of magnitude heavier than an electron. And why does that matter? Because we know that a massive particle has a wavelength associated with it, a matter wavelength, also called the de Broglie wavelength, that's just given by Planck's constant over the momentum p. Okay, and a massive particle, p is just the mass of the particle times the velocity or speed. Okay, so if the atom is 4 or 5 orders of magnitude heavier than the electron, then its de Broglie wavelength is going to be 4 or 5 orders of magnitude smaller. Okay. So typically, in a gas, the de Broglie wavelength doesn't matter because it's usually smaller, actually, than the physical size of the atom. But if you can get the gas cold, you reduce the typical speed, and you can make the de Broglie wavelength large. And to have the gas as a whole be quantum mechanical, you really require that de Broglie wavelength, this wavelength of your massive particle, becomes comparable to a typical spacing between particles. So another challenge in creating a quantum gas is that a gas has a very low density. That means the spacing between particles can be very large. It could be a good fraction of a micron. Okay. So you need a very large de Broglie wavelength. But this is what happens when we go to 100 nanokelvin temperatures. Okay, so again, here's my classical picture of a gas of atoms. These arrows just indicate the velocities of the atoms. And we know that the temperature of a gas is just a measure of the kinetic energy stored in the motion of these particles whizzing around in here. And we can relate the temperature to the typical speed of the particle just through 3/2 kBT, where kB is Boltzmann's constant, is equal to 1/2 mv squared, where v is the typical speed of the particles. So if we look at a gas at 300 Kelvin, that's our room temperature, like the air around us, and we just do this calculation and we ask how fast are the atoms or molecules in the air around us moving, we find that they move at hundreds of meters per second. So that's jet airplane speeds. So these atoms are whizzing around about this fast. Okay. Well, that's not so good for seeing a quantum mechanical behavior, because this velocity we know is going to determine the de Broglie wavelength. Remember, it's Planck's constant over the mass times velocity. If you plug in the numbers, you get that the de Broglie wavelength at room temperature of an atom is something like 0.3 Bohr radii. Okay? And I'm going to use units of the Bohr radius as a length measure here, because the Bohr radius is the size of an atom. So in particular, it's the size of the hydrogen atom, but any other atom, it's going to be maybe a few Bohr radii. So this immediately tells you that quantum mechanical behavior is not going to be that important, because the matter wavelength is smaller than the physical size of the atom. Okay. All right, so let's look at an ultra-cold gas. You can tell that this gas is cold, one, because the grad student has a thermometer with ice on it, okay? And also because I drew these arrows much shorter. So the particles are going slowly. So temperature is directly related to the typical speed. At 100 nanokelvin, the atoms are going to be moving very slowly. If you do the math, you find out they move at a few millimeters per second, so about this fast. Okay. We have to wait. He's going. Okay, so we've got a gas of atoms where the particles are moving really, really slowly. Again, the de Broglie wavelength is h over the mass times the velocity. Now we plug in this speed, and we find that we can get a de Broglie wavelength that could be, say, 16,000 times the Bohr radii. So now much, much larger than the physical size of the atom. Not only that, this works out to be a good fraction of a micron. That means it's as large as a spacing of particles in a low-density gas. So that's how we get to a quantum gas. All right, the first quantum mechanical gas of atoms was created in 1995 by Eric Cornell and Carl Wyman. This was actually done at Gila in Boulder, Colorado. And this is their original data. These are images of 3 pictures, 3 different iterations of the experiments reaching different final temperatures. If you can read over on the left, this is a gas at 400 nanokelvin. That was their hot gas. Then they got cold here at 200 nanokelvin, and their coldest picture here is at 50 nanokelvin. And what they saw here was the appearance of something unusual. The something unusual was this spike here in the center of this gas, and that was the appearance of a Bose-Einstein condensate. And I'll talk more about that. But let me just give you some parameters for this gas. Okay. Again, here it is in cartoon form. A typical temperature, you can read off of here, is something like 100 nanokelvin. It might be a little bit warmer, might be a little bit colder, but around there. The number of particles is typically something like 1 million. So 1 million atoms making up this little puff of gas. And it has a density of about 10 to the 13 particles per cubic centimeter. So this is a very low density. If you compare to the air around us, this is about 1 million times less dense. Okay, so this is a low density gas. That's actually important. These pictures were taken of a gas of rubidium atoms. Okay. Rubidium is actually a solid at room temperature. But regardless, any substance, if you go toward absolute zero, it wants to be a solid, or maybe a liquid in the case of helium, but nothing stays a gas. So keeping the density of the gas very low is important to enable a metastable state, this quantum gas, okay, that lives long enough that you can probe it, you can manipulate it. Actual time scale, it lives for, say, several minutes, which is long for the time scale it takes to produce it and to study it. Okay, so let's go back to the question of why it's interesting to look at ultra-cold gases. And one motivation might be application. So I'll mention a few applications of ultra-cold gases. One is for precision measurements. So this is actually a photo taken with some interesting lighting of the NIST cesium fountain clock. So this is an atomic clock, the basis for GPS and positioning. And they use cold atoms here. And the reason they use cold atoms is because, as we said, cold atoms means the atoms are moving very slowly. It means that you can interrogate the atoms for a very long time. So if you want to measure some atomic transition as the basis of your clock, you have a long time to probe that transition and measure it very precisely. So it's great for time and frequency standards. Another application is sensors. So you might imagine that if you have a gas at 100 nanokelvin, it's going to be very sensitive to the environment. Indeed it is. This is a photograph of a gravity gradiometer, a device that measures gravity gradients, built at Stanford University. You can also use cold atoms to sense magnetic fields, so to make magnetometers, and you could use them perhaps for navigation. Okay, a final application I have on this slide is for quantum computing. Now this is an artist's conception of an experiment that was done at the Max Planck Institute. This picture is supposed to show you atoms, cold atoms, laid out in a nice array. Okay, these dots are the atoms. And then there are laser beams coming in and interrogating individual atoms to manipulate what state they're in, et cetera. And this is one architecture you could use for a quantum computer, where these cold atoms would each serve as your quantum bit, where each one could store a quantum bit of information. This is only one of a number of possibilities for quantum computing, but it is an architecture for quantum computing that is being actively pursued. Okay, so those are applications. Those are not what I work on. So going back to why it's interesting, my interest is really in using these quantum gases to study many-body quantum physics. So it's a more fundamental physics use of the gases to ask what can we learn from studying quantum states of matter in a gas. So basically, quantum many-body physics is just when you have a bunch of quantum particles. Bunch means there are many, they're quantum, and you have to throw in interactions usually to get anything interesting. But interacting systems of many quantum particles appear all over physics, of course. It's very relevant to condensed matter physics. Some of the most interesting and the most technologically relevant behaviors that we observe, like superconductivity or giant magnetoresistance, are related to quantum many-body physics, strongly interacting systems of electrons. But this is also relevant to nuclear physics, particle physics, et cetera. So what does our system bring, this new quantum system, where the atoms are the quantum particles? As Ed said in his introduction, what it really brings is a system that you can use as a model to try to learn about strongly interacting quantum many-body physics. And why is that important? It's important because it turns out that even if you understand extremely well the microscopics of your system, that is, what an atom does, what two atoms do, how they interact, what three atoms do, once you have many quantum particles interacting, that's beyond our theoretical description. We cannot describe that, okay? So you need models to build understanding, okay? Because every theory has to make some kind of approximation because this is an intractable problem. So this system, what makes a good model system is something that's accessible in the laboratory, okay? Once you figure out how to make this gas cold, this is an accessible system in the laboratory. It's one where you understand at the microscopic level all the ingredients. It's an incredibly clean system, and it's one that you have a lot of control over. And that control is what makes it a good model system. It means that you can take this very simple system, right? It's just a gas of particles moving really slowly, right? And yet you can take this system by turning on interactions into a regime where the theory's not there to describe it. You can't predict what's going to happen, okay? And you can get interesting states of matter based on the quantum mechanical behaviors. Okay, so this is the cartoon picture I used to show an ultra-cold gas. I just want to show you one photo of the lab because this is not a completely accurate depiction of what we do in the lab. this is a small portion of the experiment. You're looking at an optics table full of stuff. The part of the table you're seeing here is about 1 meter by 1 meter. And we've got, okay, first thing you notice, we've got no cryogenic fluids here. There's no liquid nitrogen, no liquid helium, no easily identifiable big steel can that's a refrigerator, right? Instead, it looks like an optics lab. And indeed, most of the work we do is we're using lasers to manipulate and control the atoms. In the middle of this part of the table here, there's a vacuum chamber. It's basically this thing. Inside there is ultra high vacuum, which means basically nothing is inside there. And it's this ultra high vacuum. Inside there, we're going to create this ultra cold gas, and it's going to be protected from the room temperature stuff around it. Actually, the wall of the vacuum chamber will be about 1 centimeter away from the cold atom gas. Okay, so 300 Kelvin, centimeter away, 100 nanokelvin. It's hard to see in this picture the atom gas, first of all, because gases are invisible, plus it's tiny, plus it's crowded. So here's this guy to show you where the cold gas is. It's right in there. Okay. I think basically now you all know how to create the ultra cold gas. So we'll move on to how do we probe it. Okay, so you have this gas. You have to hold on to it some way. Okay, it doesn't really just fill our vacuum chamber, but we'll use some kind of trap. For example, you could use light forces. This is an optical trap depicted in this cartoon. It's just a single focused laser beam, and the atoms are, a little cloud of atoms is this blue blob in the center here. So this is light, by the way, that's far detuned or the wrong color for the atoms to absorb. So the atoms aren't really scattering this light. Instead, what it is that the electric field, the oscillating electric field in the laser, is inducing a dipole moment in the atoms, and that's the force you use to trap it. Okay, so we've got atoms trapped here, about 1 million of them, 100 nanokelvin. How do we measure the temperature? So we obviously can't just take a thermometer and stick it in there, right? Because there's no thermometer that has fewer than 1 million atoms in it. So what we're going to do is use the fact, again, that we know that temperature of a gas is just a measure of the speed of the particles. Okay? So what we're going to do is measure the velocity distribution. If you want to measure the velocity distribution of a gas, all you need to do is let go of it. Right? So the gas is confined now, but if we let go of it, it's going to fly apart. And by seeing how big the gas gets, this little cloud of gas, as a function of time, we can measure the velocities. Okay, so we're going to let go of the gas, turn off the trap, and there it goes. You can see the gas expand in that animation. Now you might notice in the animation that the gas didn't just expand, it fell. Okay? We don't usually see that behavior with a gas, right? Usually you let go of a gas and it just expands, right? It doesn't fall. Why? Are atoms not affected by gravity normally? Oh, it's that the atoms are moving at jet airplane speeds, right? So the expansion is usually the dominant motion. You don't notice the falling. But of course, atoms, like any other massive object, falls. That's my reference to Newton. Okay, but here we're not really concerned with the falling. We want the velocity distribution, so we're concerned with how big this gas got, this little puff of gas, in the few milliseconds we let it expand. So all we need to do is take a picture of this gas. We actually take an optical image. We send in light that's now exactly the color the atoms like to absorb. So the atoms, this cloud of atoms is going to cast a shadow in this laser pulse, and we're going to take this shadow image of the gas. Now, once you have your shadow image taken with a fancy digital camera, you can then put it into false color. It's really not colored, okay? And this false color just indicates how dark the shadow was. So in this case, white and red are the darkest part of the shadow, which means the densest part of the gas, and blue is lower density or lighter part of the shadow. Okay, so that's the velocity distribution, and that's exactly what these images were that I showed you before, this data of the first Bose-Einstein condensate taken of rubidium atoms. Okay, so these were 3 images of the velocity distribution. They're shown in even fancier. Not only are they false color, they're also shown in sort of 3D, so you can see the shape of the distribution. So when the gas is hot, you see a sort of blob, a Gaussian-shaped distribution. That's what you expect for classical particles. It's the Maxwell-Boltzmann distribution. But when they got colder and the condensate appeared, they saw this spike in the center. And we now know this is a velocity distribution, so this spike is a bunch of atoms near zero velocity that didn't go very far in the expansion. Okay, so to tell you why that happens, we have to talk about the quantum behavior of bosons and fermions. Okay, so we're cooling the gas to where the particles, the atoms, are going to behave quantum mechanically. When particles behave quantum mechanically, there are really only two behaviors that are observed in nature. And associated with those two different behaviors, we identify two classifications of particles. So these are bosons and fermions. As far as we know, all particles are either bosons or fermions. And as Ed said in his introduction, we can easily identify them by their property of spin. Bosons have integer spin, and fermions have half-integer spin. Now, a nice thing about atoms is that they're composite particles, right? They're made up of things like protons, neutrons, and electrons. And depending on their exact composition, they can be either bosons or fermions. So with these ultra-cold gases, we have access to either behavior, quantum behavior of bosons or the quantum behavior of fermions. So what is their quantum behavior? Okay, bosons, this is how I think of them. They kind of look like this. That's their quantum behavior. They like to do the same thing. Fermions, on the other hand, a lot more interesting and fun. Fermions all do their own thing. They don't like to do the same thing. Okay. All right, so more specifically on bosons, it's possible for particles that are bosons to all be in the same quantum state. And an example of that is a laser. So the quantum particle of light is the photon. The photon happens to be a boson. Okay? And in a laser, you have these quantum particles of light that are all traveling in the same direction. They all have exactly the same wavelength or the same color. And that's a bunch of bosons in the same quantum state. Okay? All doing the same thing. And you know that this behavior of light in a laser is very different than white light, for example. Okay, so now let's go to atoms in a gas. So we know that we have to confine our gas of atoms somehow. And so for the trap, I'm going to imagine a harmonic potential, this bowl-shaped trap, because everything's harmonic to second order. That's a joke. Okay. The traps tend to be harmonic. So in this cartoon depiction, this harmonic potential I'm just showing in 1D, and these horizontal lines are the quantized motional states inside that potential, so the quantized energy states of that trap. If the gas is classical, there's a very low probability that any one of those states is occupied, and so I just show here a few atoms scattered in some of these different energy states. Okay, so that would be like white light. But now, if these atoms are bosons, and they can all do the same thing, as we cool this gas down at some temperature, some finite temperature, there will be a phase transition to the Bose-Einstein condensate where a whole bunch of atoms go into the lowest motional state, the lowest quantum state of that trap. Okay? Now you have many atoms all described by a single wave function, okay, the wave function of the ground state of that trap. This is the Bose-Einstein condensate. It is a quantum mechanical state of matter, right? It occurs because of the quantum behavior of bosons, that they all like to be doing the same thing. Okay, so back to this picture. Again, 3 images, 3 pictures of the velocity distribution. This spike in the center we said was a bunch of atoms near zero velocity. Now we know this is the condensate. This is a bunch of atoms all in the exact same quantum mechanical state, in the lowest motional state in that trap. Okay. By the way, in this middle picture, you see both the condensate plus some atoms that are scattered in some higher energy states. That's like as you go through a phase transition from water to ice, right? You can have a state where you have both ice and water mixed. Then you go colder and you have only the condensate. Okay, okay, let's switch now to talking about fermions. So fermions are pretty interesting because when you look around you, all the matter you see is made up of fermions. Okay? All visible matter is made up of things like protons, neutrons, electrons. These are all spin 1/2 particles. They're all fermions. Okay, so their behavior might be kind of interesting. Their quantum behavior is essentially the opposite of bosons. So whereas bosons can be in the same quantum state and even like to be in the same quantum state, fermions obey the Pauli exclusion principle that says that identical fermions can never be in the same quantum state. And that's why I show them here in this famous painting, all doing something different. All right, so again, if we look at atoms in this harmonic potential with these quantized energy states, for fermions, I'm going to show two different atoms, red and blue here schematically. They correspond to, say, a spin 1/2 particle. Red would be spin up and blue would be spin down. Okay. All right, this is a classical picture where I've got, again, low probability of any state being occupied, so atoms just scattered over these different energy states. Now, for fermions, the quantum behavior of fermions is not going to give us a phase transition, but we can look at how they start to behave as you go toward zero temperature. So I want to look at now at absolute zero, how would these fermions arrange themselves? They arrange themselves like this. The lowest energy configuration is putting one spin down and one spin up in each quantum motional state until filling them up one state at a time until you run out of atoms. Okay? Because they cannot be in the same quantum state, this is the lowest energy configuration. Note that this gas would have quite a bit of energy, even at zero temperature. We define the energy of the highest filled state as the Fermi energy, or EF here. And you can define also a temperature just by dividing this Fermi energy by Boltzmann's constant. So this Fermi energy, I want you to note, can be easily calculated, right? You just need to know how many particles you have and what the quantum states are, right? Because you're just filling them up until you run out of particles. This arrangement is often called a Fermi sea. I'm showing you in this cartoon a Fermi sea of atoms, but you may be familiar with the Fermi sea for electrons. I want to tell you why I think it's called a Fermi sea. I think you can think of it like this. These atoms, or these fermions down here, they really have nowhere to go, right? They're at the bottom of the sea. There are no states for them to move to. They're just sort of stuck there at the bottom of the sea. But these guys up here near the Fermi surface, it's like the surface of the sea, there are empty states above them they can move to. And at any finite temperature, in fact, there'll be imperfections in the Fermi sea. Some states that should be occupied that are not, some states up here that are occupied. And those cause ripples on the surface of the Fermi sea, those imperfections, and extend over something that's a range, that's energy range that's given by the temperature. Okay? So the Fermi sea is the Fermi energy deep and has excitations given by Boltzmann's constant times the temperature. Okay? Okay, so this is the data from my group from 1999 where we cooled down atoms that were fermions. So we just chose an atom that was convenient for the cooling that had an isotope that's a fermion. So these are potassium atoms. And we're looking for this Fermi sea behavior to emerge. And we have atoms in two different spin states. So these are the velocity distributions that we saw cooling down. Actually, this is not the original data from 1999. But these are velocity distributions of a Fermi gas cooling down where the temperature is here marked not in absolute temperature, but in units of the Fermi temperature. And as you go below the Fermi temperature, so T over TF below 1, you expect Fermi sea to start emerging, or this quantum behavior to start appearing. Well, it's kind of hard to see it in these pictures. Unfortunately, it's not like the Bose-Einstein condensate that just leaps out at you with this giant spike in the center of the cloud. But we can draw artificially ovals on here that indicate the Fermi energy. Remember, the Fermi energy we can just calculate if we know the states of the trap and how many particles we have. So I draw that oval here. By the way, the reason it's not a circle is that the trap is not spherical and it just hasn't expanded long enough. If we let the gas expand longer, it would be a circle. Okay, but you can see as you cool the gas down, you start to reach a situation where most of the atoms are below this Fermi energy as drawn on here artificially. If we look in detail at the shape of the distribution, so this is taking one of these images, actually this one near T over TF of 0.1, and just averaging around an angle. So it's an azimuthal average around. This is how dark the shadow was, or optical depth, as a function of the distance from the center in this average, okay? So the points here are the data. The blue line is what happens if you fit to a Gaussian. So a Gaussian is the distribution you expect for classical particles, the Maxwell-Boltzmann distribution. And you can see it doesn't fit perfectly, whereas if you instead fit to a Fermi distribution, what you expect for fermions in a harmonic trap, you get this red line, which goes through the data points. Okay, so you can definitely detect that this gas is behaving quantum mechanically, and it's following the behavior of fermions, but it's not exactly as satisfying as the Bose-Einstein condensate. Okay, no, condensate shown this way would have a giant spike right here. Now, some of you might be thinking, when I studied statistical mechanics in my physics class, they told me that fermions have this distribution like this, right? The occupation in momentum, or this is wave vector k, everything's occupied at low k, and then there's a Fermi step, and nothing's occupied above that, right? That's the t equals 0 Fermi distribution. It's just this function. Oh, and by the way, this is in wave vector k. You can define k Fermi just from the Fermi energy. So is this familiar? Right? Okay, so why don't we see this? So one reason might be we're at finite temperature, right? This is an absolute zero picture. What if you're not at absolute zero? You're T over TF of about 0.1. Well, it would look like this, okay? So there's still a step there. It's a little bit rounded out. How much it's rounded out is given by the temperature. But our data doesn't look like that either, right? It looks way more smeared out, right? It looks almost Gaussian. Okay, so the reason we don't see this is this textbook example is for a homogeneous gas. That means a gas in a box that has a given density, right? A fixed density. Instead, we have a trapped gas, okay? Our trapped gas would look like this if we could measure not the occupation in momentum, but the occupation in harmonic oscillator states. But that's kind of hard to measure, right? And so it's because it's a trapped gas that the momentum distribution looks almost Gaussian. Okay, more specifically, it's because a trapped gas has not one density, but it has a high density in the center and will have low density at the edges, right? It's just this nice little puff of gas. And you're averaging over all these different densities, so you can't see the Fermi step. But if you could go in and probe the atoms in the center of the trap, and specifically probe their velocity distribution, you should see this Fermi step in momentum. And so this is something we've done fairly recently. This was published only a couple years ago, where we could see the Fermi surface, this more textbook-like shape, by probing the center 16% of the atoms. So only the center 16% of the gas that was sitting right there in the middle of the trap. Looking at their velocity distribution, we now see occupation of 1, stepping at the Fermi momentum down to 0. The width of this is now largely a measure of the temperature. Okay, the fact that we're T over TF of about 0.1. Okay, so everything I've told you so far is just the quantum behavior of atoms in a cold gas. Okay? I haven't talked at all about anything that requires interactions. But interactions is what makes many-body quantum systems interesting, right? Interactions make things happen. Interactions are necessary to make things where I can't draw theory lines and just tell you what we'd expect to see. So I want to talk about a phase transition to a state of matter with fermionic atoms that depends on interactions, and that's the Fermi condensate. Okay, so first, if you have atoms that are very cold, how do they interact? These are neutral atoms, okay, electrically neutral. Only way they interact is by colliding, okay? So most of the time in the gas, they don't feel each other at all, right? Only when they happen to encounter each other up close, then they feel some van der Waals forces. All right, so it's a short-range interaction. It only appears when particles collide. So in this field of study of ultra-cold gases, we've learned how to control these interactions. And this was from ideas that came out first theoretically and then were realized in experiments. And basically the idea was to go to a resonance in the collisions. And usually this resonance can be controlled in the lab with a magnetic field. So tuning the magnetic field over a small range around some special value, some resonant value, you could make the collision cross-section go way up. So you have very high rate of collisions, and it turns out that means you can make the interactions extremely strong. And by tuning your magnetic field, say, to just one side of the resonance or the other, you could change the sign of the interactions, whether in the many-body system they are attractive or repulsive. Okay, so we can take a system, say of potassium atoms, that has naturally a weak repulsive interaction, and we can change the sign of the interaction to make them attractive, and we can change the magnitude of the interactions basically to be infinitely strong by going right on top of this resonance. And when you do that, you can realize the Fermi condensate. This is a phase transition to a quantum state of matter where we start with fermionic atoms, and yet we can produce pictures that look a lot like the pictures of the Bose-Einstein condensate. Now, Fermi condensate, you should be thinking there's something wrong with it, right? Because by condensate here, I mean all particles in the same quantum state, right? But I told you identical fermions can never be in the same quantum state. If I told you I started with atoms that are fermions, right, how could I possibly see a condensate? I'm obviously lying to you. Okay, but you might remember, Ed told you, that it's possible to make fermions behave like bosons if you pair them up. So remember, fermions are half-integer spin particles. So if you put two half-integer spin particles together, that composite particle has an integer spin. And so a pair of fermions behaves like a boson. And so that's a way to start with a system that's exhibiting the quantum behavior of fermions and introduce a little bit of the quantum behavior of bosons. Okay, and as I told you, this behavior is not new in these, this is not the first time it's seen. It's well known from systems of electrons where they can pair up, spin up and spin down electrons pair with equal and opposite momentum and Cooper pairs, and that's responsible for superconductivity in metals. Okay, so what was the lie? These images that I showed you were not images of the individual atoms, but instead they were images of atom pairs. And it was by looking at the velocity distribution of the atom pairs is how we could see a condensate, this spike in the center, a bunch of particles, now pairs, in the same quantum state. Another difference in these images compared to the pictures I showed you earlier of the Bose-Einstein condensate is that these three images are taken not at different temperatures, although we could have done that. But to emphasize the importance of interactions, these are actually images taken at the same temperature, or at least starting at the same temperature, but changing the strength of the attraction between spin-up and spin-down atoms that would cause them to pair. Okay? And as we increase the strength of interactions at a finite temperature, we go through the phase transition to the Fermi condensate, so-called Fermi condensate. Oh, by the way, I should mention this thing is a superfluid, okay? So much like a superconductor, except it's not electrically charged. Okay, so it's a superfluid. But I want to point out that this superfluid of atoms is very different than superconductors in that superconductors always start with a nearly perfect Fermi C. That is, this step function really looks like this because the transition temperature to superconductivity is typically much, much less than the Fermi temperature for electrons. In fact, it's usually something like 10 to the minus 5. Okay? Whereas we already talked about the atom gases, where our lowest temperatures are around T over T Fermi of 0.1, which means this step is always going to be rounded out. Okay. And this is basically sets the size of these ripples on this Fermi C. So let's look at this in a Fermi C picture to try to convey to you why this is an important difference. Okay, so superconductivity of electrons. This is well described by a 50 or 60-year-old theory, the Bardeen-Cooper-Schrieffer theory, or BCS theory for short. And it really applies when your transition temperature is negligible compared to the Fermi temperature. So again, something like 10 to the minus 5 typically. So the Fermi C has ripples on top of it at finite temperature. Now those ripples are pretty small, right? Because temperature over T Fermi is very small. So here are the ripples. Nonetheless, those ripples cause resistance, right? Here, electrical resistance. When when you go through the transition to the superconductor, these ripples go away. Basically, these small imperfections near the Fermi sea are taken away by this attractive interaction that causes pairing and causes these pairs to behave like bosons. So you're only trying to get rid of some small ripples, so you only need a weak attractive interaction, and the pairing that's important is really only occurring right near that Fermi sea, okay, in a tiny region near the Fermi surface. All right, now let's look at superfluidity or Fermi condensate in an ultra-cold gas of fermionic atoms. Here, our transition temperature over the Fermi temperature is almost a 0.2. Okay, that's huge. This is why we could see it, right? Because we're only reaching down to temperatures about a factor of 2 lower than that. So this picture is clearly not right. It really looks more like this. Okay, you've got distortions of your Fermi sea, imperfections of your Fermi sea that have an energy width that's now a sizable fraction of the Fermi energy, okay? That immediately tells you that in some sense, you really want to think about this as a high temperature superfluid. Obviously, the absolute temperature is ridiculously low, but it's high temperature in the sense that you're not very cold compared to the Fermi temperature, and so you have big imperfections in the Fermi sea, and you need very strong interactions to get rid of these imperfections to create your superfluid. Okay, just in a little bit more detail how we think about this. When you start thinking about making superfluids with fermions, you're really thinking about how to make pairs, how to make these bosons. The BCS way, or the way that works in superconductors, is really a very good Fermi sea and pairing near the Fermi surface due to some weak attractive interactions. But we have atoms. So atoms are different than electrons. If you think about pairing of atoms, all of a sudden you realize you can have a real bound state of atoms, right? It's called a molecule. It doesn't exist for electrons. So you can actually make a system where you just bind your fermions pairwise into molecules. Those molecules would be bosons and should form a Bose-Einstein condensate. These are two very different ways of thinking about pairing, right? This is a Fermi system predominantly with a tiny bit of bosons mixed in. This is a Bose system, right? The fact that the atoms inside the molecule are fermions is completely negligible. Our Fermi condensate lives in between these two, okay? It lives in what's known as the BCS-BEC crossover. This is an idea that's been around, again, for something like 50 years. And the idea that these two would be limiting behaviors of the same physics. This is a very powerful idea because, remember, transition temperatures from here to here would vary by like 5 orders of magnitude. Interaction strength, sort of the strength of the pairing could vary by much more than that, maybe 8, 9, 10 orders of magnitude. Okay, but if these are two limiting behaviors, then there's something that happens in between. That's exactly the region that we can access with a gas of atoms, with a gas of fermionic atoms. And in fact, we can move just a little bit in this crossover, a little bit more toward this limit, a little bit more toward this limit by controlling that interaction strength. Okay, finally, I want to show you some visualization of the pairs, some artist conception. And this is important because what's interesting about this quantum behavior all comes in the pairing of fermions, and sort of to what extent these pairs really behave like bosons. They are not exactly equal to a boson unless they're really tightly paired into molecules. And so how do we picture this? This picture illustrates the molecule idea. This is not what's happening in our Fermi condensate, but it's the way you might think about pairing as a first pass. All right, so what I've got here are fermions. They're the people. I've got two kinds, pink shirts and white shirts. Those are spin up and spin down. The attractive interaction is between those spin up and spin down fermions. And you can see they've all paired up here, right? Okay, and they're depicted as dancers because somehow it's in the motion of the particles that we're going to see this quantum behavior. This is what our Fermi condensate looks like in this kind of representation. So again, I have equal numbers of spin up and spin down fermions, but now the pairs are much harder to see. This is a system where you see the individuals, you see sort of the fermions, but they are all paired. Here's a pair right here, here's a pair, okay? So you can see they're all paired. The reason they're harder to see is because the pair size, typical spacing of particles in a pair, is comparable to the spacing of the individuals. And so you get intervening individuals within a pair. This is what's happening in our gas. This is what happens in the crossover. You have fermion statistics and Bose statistics somehow both playing a very important role in what's going on in the gas. Okay, I have one last slide which just shows you what are we working on now. So this is my recent work slide, and I'm just going to give you an overview. So we are continuing to study this BCS-BEC crossover with the Fermi condensates. We're actually focused now on the normal state. That is, what's the state of the gas above the transition temperature to the superfluid. And the reason that's interesting is because we want to know, in the normal state of the gas, before it's a superfluid, is there pairing or not? Is your fundamental excitation fermionic or is your fundamental excitation bosonic? And we know in the limits those have to be right, but how do you cross over between bosonic and fermionic excitations? As Ed mentioned, we have a large effort now in studying ultra-cold molecules. The molecules we make are fermions, of course. Why wouldn't you pick the more interesting quantum particle? So you can see I've changed my gas here to be molecules. And that's what our molecules are. They're diatomic. Our molecules are polar, meaning they have an electric dipole moment. So I think one of the things that's most interesting is to look at behavior of a gas that now has long-range interactions, where two particles, even at a typical spacing in the gas, already feel each other, and ask, for example, could you get pairing and superfluidity driven by these long-range interactions? And then finally, I have a collaboration with Eric Cornell where we're looking at Bose-Einstein condensates now so that they don't feel left out. But we're asking what happens if you take them to strong interactions. A challenge here is the condensate really doesn't like strong interactions. So we're doing dynamic experiments where we ask, if you suddenly turn on strong interactions, how long does the thing live? What happens before it goes away? Okay, so I've been showing this is my cartoon picture of the grad students. They don't really look like that. They're a much more handsome bunch. This is just the current group of, these are grad students and undergraduate students in my group now. Okay, and with that, thank you very much for your attention. I'm happy to answer some questions.
And then there's one more, which is what brings us here today, the Institute of Physics Isaac Newton Medal, which is awarded to a person of any nationality for outstanding contributions in any area of physics. This is the Institute's most prestigious award. Previous winners are John Pendry. I list the names because I think you will know them all. John Pendry, Martin Rees, Leo Kadanoff, Ed Witten, Alan Guth, and Anton Zeilinger. So this is a list where Debbie certainly belongs, and I'm delighted that she's joined the list, and it's my great pleasure now to introduce her to talk about ultra-cold gases.
Okay. Thank you very much for the very kind introduction, and it's certainly my pleasure and honor to be here today and to have a chance to tell you a little bit about some of my research. So I'm going to talk today about ultra-cold gases. It's not going to be a comprehensive talk. I'm not going to talk about everything about ultra-cold gases, but just some of the things that I've worked on. This is a picture of JILA, this Joint Institute of Laboratory Astrophysics. It's a joint institute between NIST, the National Institute of Standards and Technology in the US, and the University of Colorado. All right, so what I'm going to tell you about today is just a gentle introduction to ultra-cold gases, what they are, why they're interesting, extremely little on how we actually make them and manipulate them. Then I'll talk about some of the quantum behaviors that we see, the quantum behavior of bosons and fermions, and I've highlighted the one I prefer. All of this is to get to the point to tell you about the Fermi condensate, which is something that we are continuing to study in the lab today. Okay, so ultra-cold gases. So I'll start with just a little bit of motivation, why you might be interested in what happens at very low temperatures. That's what I mean by ultra-cold, extremely low temperatures. And basic motivation is just that you can see new phenomena if you go to some extreme regime. And temperature is one regime you could look at. You could go to very high energies, like a particle accelerator, or you could go to very low energies or very low temperatures and ask what happens. So just to motivate this a little more, let's look at say, a temperature at the surface of the sun. That's about 6,000 degrees Celsius. And I want you to imagine that you're a scientist that lives on the surface of the sun. Okay? So this is your ambient temperature. This is what you see every day. You look outside. What do you see? You see everything is a gas or a plasma. But since you're a scientist, you have a laboratory there on the surface of the sun, and you're able to reach much lower temperatures. So now what can you see? All of a sudden you see things that you've never encountered, things like solids and liquids, the things that we're used to here on the surface of the Earth. Okay, so this just gives you an example of if you go to some extreme temperature that doesn't exist in your ambient environment, you might find some new behaviors, particularly of matter. So we're going to start here as this is sort of our room temperature, certainly if you live in Colorado, and ask in a laboratory, can we get to lower temperatures and see how matter behaves? Okay, so in talking about temperature, it's useful to use a Kelvin scale, so just the Celsius scale shifted so that 0 is absolute 0. And I have a thermometer here marked in Kelvin, but it's marked in powers of 10 or logarithmic scale, so every number is a factor of 10. So if we just put on here the two temperatures we just talked about, we've got our room temperature at about 300 Kelvin, and going up on the scale that far, you get up to the temperature of the surface of the sun. So very different behaviors, changing by that much on this scale. Let's put some colder temperatures on there. The first one I'm going to put on there is the lowest temperature you find in nature. Okay, so that, of course, is in outer space. It's the cosmic microwave background.
Is a half integer. Probably most of you know that particles with integer spin are called bosons, and they have the property that they like to all do the same thing, and when you put them in that state where they are doing exactly the same, that's called a Bose-Einstein condensate. So what she did was make a Bose-Einstein condensate without using bosons. So this is an interesting and important achievement. And the trick is to make these fermions, which have half integer spin, pair up. Once they make a pair, then the pair has an integer spin, and then after that they're able to Bose condense. So she made the first exploration of what happens as the atoms cross over from being separate fermions to paired up bosons. And in the course of that, she developed and perfected the use of something called Feshbach resonances, which allows one to control the interactions between the atoms and how strongly they interact with each other. Some people have noticed that this pairing behavior is an important thing to study because it's exactly what electrons do in superconducting materials and what helium-3 does in superfluid helium. But the difference with the atomic gases that Debbie has developed is that you have tremendous control over all of the parameters of the system, including, as I told you, the strength of the interaction between the particles. So this makes her lab has become a kind of test bed for understanding and studying how particles interact in this kind of quantum many-body system, and do the fermions pair up and form a Bose condensate. In a separate experiment, she's looked at how bosons interact, how a Bose condensate made of bosons works when you control the interaction between the particles. And she was the first to demonstrate and measure a thermodynamic property called contact, which was theoretically predicted.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.
Good evening, everyone. It's great to see a full house here. My name is Ed Hines. I'm a physicist from Imperial College, and I'm here to introduce the prize winner this evening, Debbie Jin, whose work I've followed from, well, I'm old enough to say I followed it more or less from the beginning. And so, by way of introduction, let me just tell you a few things about Debbie that she would be too modest to tell you herself. She graduated from Princeton University and got her PhD from the University of Chicago. She is now a fellow at the National Institute of Standards and Technology, which everybody calls NIST in America. That's the American equivalent of the National Physical Laboratory. And she's a professor at the University of Colorado. She leads a group in JILA, which stands for the Joint Institute for Laboratory Astrophysics. JILA, I would say, is a leading institute, possibly the leading institute, for atomic physics. In 2003, her team made the first Bose-Einstein condensate of fermionic atoms, that is to say, atoms whose spin to be something that you could say general about complex systems with strong interactions. But finally, I want to mention one other of her experiments, which grew out of the study of how bosons interact with fermions, so spin integer and spin half integer interact with each other. And so that's developed in collaboration with Jun Yi, who is also at JILA, into an experiment that has allowed her to make ultra-cold polar molecules with a density and a temperature way beyond what was previously possible. And this has made the quantum gas of polar molecules a really important new research tool. I think she'll probably talk a little bit about these potassium rubidium molecules. With these, she's able to control the chemistry. So if one of these molecules approaches another one, she can put them in a totally defined quantum state and control whether these molecules interact or not. So this is fundamental control of chemistry, which I think is very interesting for a physicist, at least, though we were just discussing you're not going to make kilograms of stuff this way. But nevertheless, it's important, I think, for understanding basic things about chemistry. The significance of all this has been recognized by a lot of awards. I'll list you just some of them. In 2003, she won the Physics MacArthur Fellowship, which some people call the Genius Grant in physics. She won the Rabi Prize of the American Physical Society in 2005, Benjamin Franklin Medal in 2008, Gold Medal of the US Department of Commerce in 2011, the L'Oreal UNESCO Award for Women in Science in North America in 2013, and the Comstock Prize of the US National Academy of Sciences in 2014, this year. She has been elected to the US National Academy of Sciences and to the American Academy of Arts and Sciences. Okay, that's a long list of awards.